Okay, good morning. Welcome to
Math number 847.
Math847. So today we're going to go on a little last second vacation, and I decided we're going to do just kind of a light exercise today. It might be 3 videos worth, but we're going to study the introduction to something called quadratic reciprocity, which is kind of an advanced idea in number theory, and it's sort of the first advanced idea in number theory that we've seen. So this is a table of how the number n squared minus 5 factors. And I got this off of Wikipedia.
Alright.
Okay, so if n is 1, 1 squared minus 5 is minus 4. If n is 2, 1 squared minus 5 is minus 1. So we're not going to worry too much about those two. But then 3 squared minus 5 is?
That is 4.
Okay, and what is 4 squared minus 5?
That's 11.
What is 35 squared minus 5?
1,220.
Okay. All right. And then the third column shows how the numbers factor. So, for example, can you show me how 23 squared minus 5 factors?
2 squared times 131.
Very good. All right. So now we have this chart in front of us. And this chart is what Wikipedia was using to illustrate, I think what they said is some subtle patterns in these factorizations involving quadratics. So do you notice anything about the factorizations of these numbers when I factor n squared minus 5 into primes?
So, I'm noticing, I don't know if this might be a coincidence or not, but I'm noticing that we have a lot of things that end in 1 and 9. Like, we've got 31, 11, and then 59, 19, 19, 29, 139. We have 41, 191, 11, 251, and 71.
Mm-hmm.
So these alternating sections of 9s and 1s. But it looks like when we have a 1, we have something that ends in 1, we don't have something that ends in 9. Actually,
Well, we have
never
11.
mind, we have 11 times 29.
Okay, but at least it's...
It looks like for the most part that the 1s and 9s are separate.
Yeah, and here's another one. Here's 19 times 41, 11 times 19. But that's a good thing to notice. All right, do you notice anything else?
Well, it seems to be that the only other primes involved are 2 squared and 5. Those are the only other ones I see.
Okay.
Except for minus 1 right here.
Yeah, it's minus 1 and minus 2. We don't need to worry about those so much. Maybe those are special cases, but who knows, maybe they're not. So what does that mean?
Well, the ones with 2 squared and the 5 are divisible by 20, so they're going to end in 0.
Yeah, that's true.
I also see that at 45 you haven't gotten to a number that you had to express with more than 3 primes yet.
No, that's interesting. Yeah. Blanking on the name of that theorem. There's a theorem called the Erdos Katz theorem that talks about the number of primes you need on average to factor a number. And it somehow relates to the size of the number. But anyways, it's true we don't see a lot of prime factors in these numbers. You're right about that, but that could be that it's just the numbers are small. We're only getting up to 2,000, so
Yeah.
it's hard to factor those into lots of it's hard to factor 2,000. The most you could factor it into would be 11 primes, because that would be it's around 2 to the 11th. So it does stay small.
I'm also counting like unique primes.
Yep. Yeah, I think the Erdos Katz term actually doesn't count unique. I think 2 squared times 5 times 101 would be 4 primes. I'm not an expert though in number theory. But you're right, we always seem to see, we occasionally see the 5 and the 2, but what primes do we not see?
We haven't seen a 3.
Ending in 3 or 7.
Are there primes that end in 3 and 7?
Well, just 3 and 17.
There's like 7, there's
23.
17, 23, 37.
Okay, so there are definitely
So
lots of
there are.
primes.
We're not seeing them.
We're not seeing them, and that's kind of a surprise.
Mm-hmm.
That when you look at n squared minus 5, you don't see primes that end in 3 and 7. Or 7, I mean. But you see lots of primes that end in 1 and 9. And you also see the 2s and the 5s.
Yeah.
Alright, so let's go on. Let's see what squares look like when we look at